perfect that Andy was talking today about the zeta vacuum. And just to make it very, very explicit, these are the same zeta vacuum and this zeta parameter that gives rise to the axiom. And indeed, we already yesterday looked briefly how this Patrick Winn mechanism to resolve the zeta problem could work. The idea being, well, if zeta is a parameter, you really can't change the energy. But if it's a dynamical degree of freedom, then a field can actually evolve, and that basically allows the field value to explore its energetic minimum. And as it turns out, this energetic minimum is at the value where Cp is conserved, and the observable electric dipole moment of the neutron is actually essentially zero. Just to remind you, of course, if you have a dynamical field, you of course also have a particle associated. Okay, so that's what we explored a little bit yesterday, but yesterday we did it in pictures, so let's today actually briefly at least have a look why the zeta being zero actually corresponds to the state of lowest energy. And I'm not going to basically calculate the full potential because that's obviously a rather hard problem, but what you can do is you can at least give an argument why the Cp conserving value, or zeta, equals 0 is actually basically the global minimum of the potential. So we have our ingredients, we made it a dynamical degree of freedom. We insist that zeta does not have a tree-level potential. So classically, all values of zeta are equal and have equal energy. And that, of course, implies that zeta actually couples to other fields only via derivative terms. So basically, if you want to have coupling to fermions, for example, you only have coupling via derivative terms. And we'll come back to these properties a little bit later, because these properties actually tell us a lot of what type of particle this zeta has to be. Okay, but let's first find out why zeta equals 0 is actually energetically preferred. Well, what we can do is basically what we can calculate is the effective potential, or the effective energy, or free energy as you will, basically of as a function of this field value zeta, which we now basically as the parameter take to be completely constant in space. So the field value now, zeta, is now the same value everywhere in space. And that is basically what you would call the effective potential of this V of zeta. So basically, the effective potential gives you the energy as a function of the field value, or more precisely, the energy as a function of a spatially constant field value. Okay, and what you can do now is you can write down a path integral expression for this potential, and the path integral expression in a rather kind of sketchy way is an integral over all the Gluon fields, and then you have an action that contains basically everything except for our coupling of zeta to the gluon and the gluon field strength dual. And now these properties come in because this action that basically contains all the rest of the standard model the Higgs fields, the fermion fields, and so on, as well as importantly the gluon fields. Because the theta has no tree-level potential and it only has derivative coupling, so if we take a spatially and time-wise constant field, basically theta does not appear in any other term than in this coupling to the G-dual term. So basically, this action does not contain theta. It contains everything else, gluons, other fields, and so on, but not theta. Moreover, and that is a small assumption I'm going to make, I'm going to assume that theta is the only source of CP violation. So basically, what I'm doing is basically rotating all, or pushing all in a sense, the quad mass effects with all their phases that we briefly had yesterday, and putting them all into this coupling to GT duals, and we'll see in a second how this can be done in principle. So in that sense, this effective action here is actually real. So it's basically CP conserved and therefore real. Okay, so this is basically the path integral expression for this effective potential. And now you can make one of the kind of very few, more or less, strict arguments about kind of the path integral. Well, what you can do is basically, well, this energy here is real, and in Euclidean space you have e to the minus this potential, so this thing is real as well. So this is actually quite nice, because now you can say, okay, if I put or take an absolute value of this quantity, it shouldn't change. So basically I can put absolute value signs over here. And now it's just a clever application of kind of the triangle inequalities that you use for ordinary integrals. Because if you basically take the absolute value signs and you pull them into the integral, the whole thing only gets bigger. Because now you're, instead of having some potentially oscillating or negative and positive contributions, you only have positive contributions. Okay. And now it's actually rather straightforward, because now you can put absolute value signs in here as well. So you have these two factors, basically the standard model action and the theta term. So basically you have put them into one exponent, but it's not convenient to put them into two, just using the law of exponentials. And now if you put modular signs here, you have the modulus of this e to the minus s effective, as a e to the minus of the standard model action, and the modulus of that is actually, because it's assumed to be real, this is again just e to the minus s effective, so that the modulus sign doesn't do anything. Now this thing over here, if you put the modulus sign here, well, this thing, you actually already heard from Andy today, that this thing here is a topological quantity. So it's an integer, and it's in particular real. So that means this thing in total is a pure phase. It's completely imaginary in here. So e to the I something is a pure phase, and if you take the modulus of it, it's just equal to 1. So this thing drops out. So that's why it's gone over here. And now you can just compare to the expression that you started with, and this thing over here is exactly the same as if you had set theta equals 0 right from the start. That would be basically putting here just theta equals 0, everything drops, and you get exactly the same expression. Well, and now you use, again, your expression for your effective potential, and you find that basically this is nothing but the exponential exponential, and I should actually put have equal signs here, sorry. And so this is equal to e to the minus the potential at 0. And now you have a nice inequality between here and here. You can take the logarithm and basically use the minus sign, and what you find is that, of course, due to the minus sign, the inequality somehow turns around, that the potential at theta equals 0 is less than the potential at any other value for theta. So theta equals 0 is the energetically preferred state for QCD. So in that sense, that is the state of lowest energy. And you can easily imagine, just by looking at this expression here, that actually this inequality is strict, because you get phases as soon as you basically have theta not equal 0. So as you move away from theta equals 0, actually the potential does indeed go up and acquire larger values. There might be special points of theta where it's again more or less the same, but locally around theta equals 0, it's going up. So in that sense, it's a true global minimum. And that is basically now, in a sense, really the kind of, not fully quantitative, but at least filled with a proper, strong argument about the effective potential argument, why this theta value will now evolve to its energetically minimum if theta actually is dynamic. And that basically ensures that Cp is conserved and the electric dipole vanishes. One more comment. In these arguments, I've always used theta. And theta is a dimensionless number. However, if you want to deal with a field, and the only type of field theta can be is a scalar or a pseudoscalar field. If theta is, and it will turn out to be a pseudoscalar field, then the properly canonically normalized field should have dimension 1. So you can do that, and more formally do that, actually based, for example, on the toy model I will do in a second. But the properly canonically normalized version is that you actually have the field, which you can now call A, divided by some scale, and this scale will turn out to be a scale of spontaneous symmetry gradient. That this is actually theta. So then you have a proper dimension 1 field over here. So that is just a process of canonical normalization. Okay. The question remains, what kind of particle actually does have these properties? And we already had the properties listed over here. They, of course, also apply just as for theta, they apply for A. But we actually have another property, if we think about it, because as this quantity is really this topological charge that is always an integer, so this is always an integer. If you have this property, then theta or A over Fa is just actually defined, or actually makes a physical difference only basically up to shifts of 2 pi. Basically theta and theta equal 2 pi, or theta equals 1 and theta equals 1 plus 2 pi are physically the same. They have the same energy and everything. And you can, of course, see that over here, if that is an integer and you shift theta by 2 pi, well, you just get an additional phase that is actually 1. And therefore, there is no physical difference between theta and theta plus 2 pi. And these properties that you now have listed here are suggestive of a particular type of particles. What type of particle actually does live on a field range that is basically from 0 to 2 pi? Well, you could imagine 0 to 2 pi is essentially a circle. And the one particle that comes to mind that lives on a circle, or the one field, is actually a Goldstone boson. Because if you imagine your Mexican head potential, the Goldstone mode is exactly the one running along the bottom of the potential, and this is of course a circle, and therefore the field range of the Goldstone degree of freedom is actually something like 2 pi times, well, the radius of the circle, and the radius of the circle is just a vacuum expectation value of the field that is spontaneously broken. So basically, a Goldstone boson of a U1 symmetry that is spontaneously broken with a VEF that is Fa actually has exactly this property for the field range. Well, we also know that Goldstone bosons, because of symmetry, have at best derivative couplings, and of course, going along the bottom of the potential, because it's a symmetry, all field values are equal, they all have the same energy, and that means Goldstone bosons do not have a tree-level potential. So in that sense, it's clear that a Goldstone boson is actually a suitable kind of particle to make it an axion. Okay, but of course we cannot pick just any random Goldstone boson. That would be a little bit too easy. Our Goldstone boson has to have one special property in addition to all these. It has to couple to the gluons in that way. It has to have this coupling Goldstone boson times this quantity. And the question is, how does this coupling arise? And let me try to at least briefly sketch how this comes about in a kind of very simplified toy model that has at least the essential features of a proper axion model. And the toy model is actually just kind of a QED, so it's a U1 gauge symmetry. It has a fermion that is charged under this U1 symmetry, and it has a U1 charged scalar field that is, however, charged not under the gauge symmetry, but it's only charged, so that is the gauge symmetry, so that is just the usual phase shift. No, sorry. I forgot to write the gauge symmetry, sorry. In a sense, the scalar field here is charged under a global symmetry, basically that is shifting the phase of the scalar field. And the fermions, in addition to the usual gauge symmetry, that is basically just shifting the fermions by a phase, there is now an additional U1 symmetry that basically rotates, again with a phase, the kind of fermions, but, and that is the non-trivial thing, here you have a gamma 5. So it rotates the left-handed fields in one direction and the right-handed fields in the other direction. And that is different from what you would usually call a U1 gauge symmetry like electrodynamics. There, left and right are basically rotated in the same direction. So this is an axial symmetry where left and right are actually rotated in exactly the opposite direction. So this is a global symmetry of this Lagrangian over here. And in addition, you have the usual gauge symmetry, basically, where the fermions are all, basically, it's left and right are all rotated in the same direction. But actually, the scalar is not charged under this gauge symmetry, so that is important. Okay. You can basically also, of course, couple this scalar to the fermions and basically still preserves the symmetry. But what you can now do is you can basically take the potential to be a Mexican hat potential. And if you do that, you get spontaneous symmetry breaking. And you can check you are basically spontaneously breaking this axial U1 symmetry. So you're basically doing a spontaneous breaking of this global symmetry, not of the local one, because the scalar field is not charged under the local symmetry. So under the local symmetry, it's completely neutral. Whereas under the global one, it's charged, and therefore you get spontaneous symmetry breaking of this global U1 symmetry. And because it's a global symmetry, the phase gives rise to a Goldstone boson, and this is really the Goldstone boson that we now want to use as an axiom, so to speak. So far, however, we only have the Goldstone boson. It doesn't give us this crucial coupling to FF dual or GG dual. In our case, because we only have a one gauge symmetry here, it's really FF dual, but the whole argument in a more elaborate model for GG dual for the QCD would go exactly in the same manner. Let's have a look at this FF dual coupling. Okay. The most naive thing that you can do is you could basically draw a diagram where your Goldstone degree of freedom goes into a loop and couples to the photon. And it's a loop of fermions, and basically then you can calculate an effective coupling of your Goldstone mode to basically these two gauge bosons over here. And then, basically, without even calculating in detail, this kind of diagram, you quickly check that, well, if you have a Goldstone mode, which is a scalar, coupled to two gauge fields, the kind of lowest order operators that you can write are couplings to FF dual and F squared. And now it's just a matter of choosing the right parity, what you get. And since this basically is a suitable axial symmetry, you basically get a pseudo-scalar Goldstone mode, and that means this would couple to F dual, just to conserve parity. The original dimension didn't have any parity violation. Okay, you can also give the kind of size of this coupling, because it's a coupling of a scalar field to FF dual. FF dual already has dimension 4. Your scalar field on top, you have dimension 5. So your coupling constant must be dimension full. It must be 1 over a mass scale. And if you look at this diagram, there's only one mass scale in the game, which is the mass of the fermions. And if you go back here, the mass of the fermion will be proportional to the vacuum expectation value of our spontaneous symmetry breaking. So essentially, if I now call the vacuum expectation value Fa, my coupling constant will be something of the order of 1 over Fa. And that is exactly the type of coupling that I want for my axiom. That said, you can actually also look at this slightly differently, and that is perhaps even more illuminating. You have here a triangle diagram, and triangle diagrams can perhaps remind you of something. So any suggestions what triangle diagrams usually do? Anomaly. Exactly. So you have an anomaly. And this is something, if you think a little bit about it, that you should have. Because after all, we want to equip our Goldstone mode, which has no potential. We suddenly want to equip it with a potential. It arises from QCD. So it seems like QCD is breaking or making our symmetry anomalous. And indeed, you can also think about this coupling in terms of anomalies, basically in terms of the Adler-Bell-Jaeckel anomaly, or, and that is actually perhaps even nicer to do, you can basically think of it in terms of the chiral rotations, and these are the chiral rotations, so these are chiral or axial rotations, and you can study the effect of such a rotation, which is supposed to be a symmetry after all. At least it's a symmetry of the Lagrangian, the classical theory. You can now ask, does the path integral also transform under this symmetry? And the one thing that is different in the path integral compared to the action is actually the measure of the path integral. So you have to look at the measure of the path integral and how it transforms under the chiral or axial rotations. And in a sense, this is basically, it's a rather lengthy calculation, that's why I'm not going to do it. But what you find, you can, for example, look it up in Pesky and Schroeder. If you do this axial rotations and you take care of all the potential divergences, what you find is actually that this measure is not invariant under these chiral rotations, but instead you get an extra term. So if you do a transformation or a rotation by an angle beta, you get an extra term that is proportional to f dual. And that is exactly the kind of term that we are aiming for. And now it's pretty simple. You just take beta equal to A over Fa. So basically, you're just taking your Goldstone mode and you rotate it in a sense away. You rotate it to 0. And that means just choosing locally the right beta. And then you get a term proportional to Ff dual, but now it's actually also proportional to your axion field. And in that sense, you now have exactly the coupling you desired, the axion field being coupled directly to F dual. And that can also be expressed now in terms of an effective Lagrangian that basically has axion F dual, and if you put all these factors together, we get something like alpha over 4 pi Fa as the prefactor, and the minus 1/4 is just a suitable normalization. So now you have exactly the desired term. And that means if you take one of these axial symmetries, you put your Goldstone boson into action, and this Goldstone boson will couple in exactly the way you need it for the axion. And therefore it's a suitable axion. Of course, this was for photons, but as I said, for gluons, it goes exactly the same way. Okay, so what does that now mean? Well, because we already saw that the energy depends on the value of theta, and therefore on the value of the axion, this U1, this axial U1, or the U1 Paget-Quinn, is not an exact symmetry, it's anomalous. That changes the Goldstone mode to a pseudo-Goldstone mode. And now, of course, it takes your initially massless particle, the Goldstone mode, and makes it a massive particle. And of course, now the phenomenologically important question is, what is actually the mass of this pseudo-Goldstone boson? Well, you can again do some dimensional arguments. What kind of scales do we have in the game? We have the spontaneous symmetry breaking scale, that is Fa. We have quark masses over here, and we have some QCD stuff. Lambda QCD or F pi. And what can you write down? Well, you already have an inkling because the coupling is 1 over Fa. And this coupling is the one that actually links it to QCD. So, in a sense, the mass should be proportional to this coupling, or the mass squared should be proportional to 1 over f squared, f8 squared. So that is a bit over here, and now you can just go ahead and make the dimensions right. You take your QCD stuff, you take some n pi squared, f pi squared, and that's the rough estimate for the QCD mass. Picking n pi and f pi is just basically kind of picking the right QCD quantities. You can, of course, calculate this again in a little bit more detail and with a little bit more care. And this is again this kind of, in a sense, QCD effective field theory, basically using pions and kind of vacuum expectation values for the quark condensate. So this is kind of current algebra stuff. And if you do that, you actually find that you get this nice prefactor over here, and u and d over nu plus nd squared. Numerically, that is not a dramatic correction, but fundamentally, it has an important feature, and that is really also coming back to what we already saw yesterday. It's proportional to the quark masses over here. So if one of those quark masses were to be equal to 0, the axion mass would vanish. And that means basically we basically would have no potential at all. But actually, we also wouldn't have a problem, because, and now I have to unfortunately use the blackboard again, but I'll try this black. You already briefly yesterday had this, that the really observable theta is actually theta bar, which is theta plus the argument of the determinant of the quark mass matrix. And you can now see something interesting, because if one of the quarks, say the up quark, is massless, the determinant is 0, because you have 1 0 eigenvalue. And that means the argument of 0 is completely undetermined. And that means theta can be whatever, so you can also choose it simply to be 0. So in that sense, theta is not an observable parameter if basically one of your quarks, or one of your quarks is massless. And remember, that actually was also explicit in the expression for the dipole moment, which had a proportionality to one of the quark masses, and therefore the dipole moment would be 0 if basically one of the quarks would be massless. Well, nature isn't like that probably. So, say 20 years or so ago, this was not clear, but by now, actually, lattice studies are pretty convinced that the up quark mass can't be 0, and the down quark mass definitely not, but the up quark mass is also unlikely to be 0. So we do have a massive axion, and we do have, in a sense, in principle, an observable electric dipole moment if theta were not equal to 0. Okay. Yeah. Yeah. So in that sense, this is really kind of talking to each other. Let me briefly comment, just one very, very brief comment, why you have this argument of the determinant of the quark mass matrix. And you can actually see that, in a sense, from this over here, because in the standard model, you can basically take all your Yukawa, basically Yukawa couplings, which couple or give mass to the quark. So basically you have Yukawa times Higgs wave times the fermions, and that's the mass term. And of course, the phases of these mass terms, they really contribute here. But you can check that such a rotation actually changes the phase of the quark mass. So this is really a phase rotation of the quark mass. And doing that, you can of course shift between the phases of the quark masses and theta, because now you can see you shift from one, you use a rotation, but you can't get it for free because you get a shift in the theta parameter. And that basically, if you write everything down, gives you exactly this combination that is basically invariant under all phase rotations. Okay, one last comment. As I said, I wasn't going to calculate it in detail. These guys actually did a rather nice calculation, actually not just of the mass, but funnily enough, they actually did the whole potential. And you can see we have our m pi squared f pi squared here, but now you have here really the potential. And just as a remark, that's why I inserted it, basically, it's not really a pure cosine, it's a sum of cosines with different frequencies. As you actually would expect from the sum over the different topological sectors, which have e to the I theta, e to the I 2 theta, and so on for the different topological charges. And a pure cosine would be something like that, but actually the potential is a little bit more kind of kinky at the top. And depending on the parameters of QCD, it could even have a proper kink, and that would be something interesting, but a little bit too complicated to dwell on today. Okay, one final argument compared to that. So this calculation is really this kind of old-fashioned current argument where you basically take the low energy Lagrange of QCD. But you can actually also go back and look at topology and relate the mass to the topology. And to do that, you actually go back to your expression for your effective potential. You take the second derivative. If you do that, you basically, just on this side, basically take two derivatives. You get the second derivative of the potential times the volume. I'm taking, again, everything spatially and time-wise completely constant. And first derivative terms. But if you evaluate theta or A equals 0, the potential is in the minimum, so the first derivative terms drop, and you get basically the second derivative of theta times the volume, and that is nothing but the axion mass times the axion decay constant, that's the normalization, times the volume, and the minus sign. So that's one side of the equation. So you take the second derivative of this expression for the effective potential. But you can do that also on this path integral side. And if you do that on the path integral side, you basically have your path integral from earlier. But let me now just for convenience write this explicitly as the topological charge Q. So you have here this exponent with the topological charge. And if you now take the second derivative, well, nothing here depends on theta. The only theta dependence is here. Taking the second derivative just brings down two factors of Q, two factors of the topological charge. So this thing here is now just this path integral, and this is nothing but the vacuum expectation value of the topological charge squared. And then you ask yourself, what could that be? Well, the expectation value of the charge squared is essentially what you would call the so-called topological susceptibility and times the volume, because everything, of course, grows with the volume. So this thing over here is really minus the volume times the topological susceptibility, and that basically means that's an axion mass. Oops, why did I have this? This minus sign should not be there. I'm not sure what I was typing. Okay, so without the minus sign, negative plus sign, the axion mass is essentially given by the topological susceptibility and that is something, for example, you can calculate directly in lattice QCD, for example. Okay, now on to, let's say, more phenomenological shores, but maybe, well, in any case, please don't hesitate to interrupt me for questions. Are there any questions right now? Okay. So let's do a little bit of phenomenology. So far, we have only, in a sense, a relation, let me go here, between the axion mass and the axion decay constant, or the VEF of the spontaneously broken symmetry. Everything else here is known, at least to some level of precision. This is really a known quantity. So what you have is the mass of the axion being proportional to 1 over the scale of spontaneous symmetry. But that is, of course, the unknown. You don't know where you need to break your symmetry spontaneously. You can do it basically at every scale you like. But you actually get one more thing from that, because if you look at this relation over here, you actually have a direct link between your scale of spontaneous symmetry breaking and the coupling to 2 gluons for the QCD axion. But you can actually do it in any explicit model, and you find the same argument gives you essentially, with basically with no exceptions, also a coupling to photons. And I'll focus on the coupling to photons because for experiments that is the more easily accessible one. It's easier to picture that. Okay, so what you can do now...
I have a question.
Yeah.
How do you get gamma A, gamma, the U1 is topological material? I mean, isn't that like a total derivative which is really meaningless?
The U1 terms, the theta U1 term, so to speak, you're completely right. That is topologically trivial. So basically, if you write a term theta F dual, and that is basically electromagnetism, so that's a U1. Then this, unless you have some monopoles or something weird like that, is unobservable. But it becomes interesting as soon as you make this thing, you move it and make it A over FA. Because now it's a field. And now it's not a total derivative anymore. Because this thing is a total derivative. But the whole thing is not.
What you're saying is that then you A to fix as 3, and then given that A, I expect other values like A, F, U, or...
You automatically get them, and these things are not total derivatives anymore because derivative actually are that.
I was just wondering where
So this term itself comes from exactly the same argument. We go back here. So it's exactly the same argument. And basically, if your extra particles, or your extra quarks, or whatever you have any electromagnetic charge, you get exactly a contribution. But that is not all of it, because due to the QCD effect, and that is what you see when you actually calculate the mass. Because you can see actually the mass induces a mixing of the axion with the pion. You get an additional contribution to the electromagnetic coupling that is inherited from the pion. And this mixing angle is not integer or any simple fraction. It's given by masses and stuff from the quarks. So it's basically impossible to have a cancellation between the things that you generate from fundamental charges, which are typically integer or some fractions, and the mixing with the pion to cancel those two. Basically impossible. You can come somewhat close, but, well, unless nature has something weird in mind, it's basically impossible to make it 0. But a good point, really making it dynamical also makes it a non-derivative term. Okay. So now, basically, what I plot here is essentially this photon coupling. You could also take it to the hypercharged bosons, but that is a minor factor in between. And basically, I'm going to use it also here in the following, basically some wildly logarithmic scales on every axis. So this is like 1/10 to the 3 GeV. This is like 1/10 to the 12 GeV as a coupling constant. And if you take into account that the prefactor of 1/FA is something like alpha over 4 pi. Alpha over 4 pi is not completely negligible, it's 10 to the minus 3. So something like here, coupling like here, would correspond to a spontaneous symmetry breaking scale of the order of 10 to the 6 GeV, and here 10 to the 12 would correspond to 10 to the 9 GeV. Okay, so that is the coupling. And here you can also plot the mass. And basically, again, widely logarithmic scale here, 1 electron volt here, a micro electron volt, say, over here. And now you can basically use this relation that both the mass and the coupling are proportional to 1/FA, and you see that a true axiom, a QCD axiom that addresses the strong CP problem, lives on a line. Basically lives on the line because coupling and mass are directly related. For the gluon coupling, this is really a one-to-one relation, and this line is really infinitely thin. For the electromagnetic coupling, you can choose some charges in the underlying model, so there are some model dependencies, and that's why this line is actually not a line, but a band with a factor of a few to maybe your extreme, a factor of 10 in both directions of variability. But essentially, QCD axons live over here. You can actually just get a comparison. The pion actually looks very similar to the axion. It also has an FF dual coupling. That would live actually somewhere over here. Okay, so you plotted basically coupling versus mass. What does it help us? Well, you can now start looking for ways to actually probe and experimentally test this concept. That's what we're going to do now. And in a sense, all these colorful things here are different experimental or observational tests. And we'll at least look at a few of them in the next few minutes. Okay, one more comment. That's why I also used, after all, there's only one parameter. You could have done a one-dimensional plot, so to speak. It might seem to be a little bit of an overkill to plot mass and coupling independently, but the idea is that if you don't need or don't want to use your axiom or axiom-like particle, and that's basically the definition of an axiom-like particle, if you don't want to use it to solve the strong CP problem, the relation between the mass and the coupling may be lost. And that'll give you some idea how such axiom-like particles could come about. But then you basically don't have this relation, and it now makes simply sense to not restrict your experiments just onto a one-dimensional line. Let's have a look and see what kind of mass reach and coupling reach experimental tests actually have.
I have a question. What is the kind of pink region near on the background of the axiom?
That one, that is the region that will come to tomorrow. That's the dark matter region. Maybe one brief comment. This, of course, actually kind of gives you also this weak coupling, light or heavy mass picture from the beginning, basically, where you can explore basically in two directions. Okay, so let's see how we can find the axiom, and let's at least try to get started on that. If you are a high energy physicist, usually, well, if your tool is a hammer, you use the hammer, and the hammer is basically some collider, but unfortunately that doesn't really work that well, because, well, axions are not easy to detect in that because their interactions are suppressed by the spontaneous symmetry making scale, and if that is large, and that makes it very, very difficult because the coupling becomes extremely weak. So, therefore, colliders might not be the real thing. You can also typically not quite manage the energies that you would want to go to explore, say, the extra quarks or extra fermions that you introduced for your Patrick-Quinn model, because TeV energies are not sufficient for that. So that is something you already know. Not so seriously, of course, these colliders are dangerous objects. So, you may have seen that, but I like that one. Just making a little bit of fun of these nuclear physicists. And then bad things happen. And you may think this is not going to happen because we already switched it on. But let's put it like this. As a not so serious comment, you want to explore higher mass particles with high luminosity LHC, and that's possible because of the PDFs. But that means also you could, of course, explore a new energy scale for your black holes or whatever. More seriously, it might be fun to think about these arguments that preclude kind of Earth-eating black holes for FCC, because they're not so obvious anymore. But perhaps the much more dangerous thing would be that one for... Anyway, okay, so how can we go about and start looking for these axions? And the hope would be to start looking at low energy experiments. And that is possible, or at least we might get a chance, because a lot of this parameter space, if you look at it here, even if you look basically in the range of the pion, it's actually relatively low mass particles. It's 100 mega-electron-volt and down perhaps. And indeed, nowadays, from experiments, you can see these limits already here. We are in the sub-electron-volt region. And that basically allows us to use collisions or whatever we do with a much, much lower energy scale. And the first type of experiment I want to briefly mention is kind of a paradigm for a lot of these dark sector searches. It's a so-called light shining through a wall experiment. And it literally tries to do what the name suggests. You take a powerful light source, typically a laser, and you shine it onto a wall. And this wall better have no holes, otherwise the experiment is no good. And then you put up a detector and you look for photons coming out of the wall. Sounds a little bit crazy, so how could it work? Well, there could be some idea that somehow your photon transforms into a new particle. The new particle being extremely weakly interacting, it basically can traverse the wall, and on the other side you just hope that it converts back into a photon. So where is the power of this experiment? Well, the power is here, because it's quite easy to do 10 to the 20 photons per second. That's a better laser pointer. That's about 10 watts of laser pointer power. So slightly dangerous if you wave it around, but nothing too special. And detecting 1 photon per second is actually also doable. You basically buy a commercial camera and put it in liquid hydrogen. That gives you about 1 photon per second. And of course you can do, with proper equipment, you can do much, much better on both sides of the game. And that means this process doesn't have to occur very often. 1 in 10 to the 20 is enough to have a detection. And that is really this power. It's enormous precisions. You can really start looking for extremely rare events. You can study extremely weak couplings. But of course, it has to work for your particle in question. So, how does it work for the axion? Well, for the axion, you now exploit the coupling to two photons, and that's why I like this coupling with two photons. It's a coupling of E dot B to the axion. And now you can basically just configure your laser. That provides you an electric field. And now you provide simply a strong magnet. You put up a strong magnetic field. The E from the laser combines with the E from the magnet, and out comes an axion. Axion goes through, and on the other side, you just invert the process. And you can calculate the probability, and unsurprisingly, basically, it's proportional to the strength of the magnetic field times the length over the mass scale that suppresses your coupling, or Fa. You can actually write the coupling explicitly over here, and the whole thing to the force power. So it's really sensitive to the magnetic field strength, the length, and the coupling. Okay, people have done that. There have been quite a few experiments. The most recent and best one is actually ALPs at DESY, that basically used a Hera magnet, so that is the Hera magnet. So they plugged it up in the middle, and laser went through, and on the other side you have a detector. And if you do that, you actually already get a quite powerful experiment. And that is basically really excluding this gray region over here. And you can see it's going down to 1/10⁷ GeV, basically a scale of 10 TeV for the scale of spontaneous symmetry breaking. So this already inches out of the directly accessible scale at LHC. And this was really a very small scale experiment, kind of commercial laser, spare magnet, and basically a CCD. And plans are to improve, let's say, by 4 orders of magnitude in the next few years. And this is, of course, really the power of this type of approach. It's not yet fully exploited. So. 2 drawbacks. You can already see the mass is limited, obviously, by the laser frequency, but it's actually more limited than that, because this length to the 4 probability behavior actually comes from a coherent effect, and you need basically some axion photon coherence, and that actually limits the mass reach a little bit more than just the energy. And unfortunately, it's also still a little bit away from the actual QCD axion, so a little bit more work is needed. Okay, I'm running out of time, but if you give me 5 more minutes, I'll briefly go and basically follow Joerg, our dear host, in making life miserable for experimentalists. Because, well, so far this looked like a nice experiment, but, already, I think, quite a few years, 20 years ago or so, and Joerg leaned back and thought, and basically that you're not going to see anything with such a puny little experiment. And the argument is relatively simple. The same process that you use for your light shining through wall also happens in the sun. You take a photon out of the plasma, and there are plenty around. You have a magnetic or electric field in the ions, you combine them, out comes an axion. And because it's so weakly interacting, it basically goes immediately out of the sun. Okay, you say, a rare process, why do I care? Well, there are 2 problems with that. This thing leaves immediately from the center of the sun. So it takes energies of the order of the temperature of the sun. So it's not an electron volt axion, it's a kilo electron volt axion. So that is something that costs you a little bit more energy. But more importantly, this is immediately out. Whereas a photon, which would set you the benchmark basically for how how long it takes to get out of the sun, the photon scatters and scatters and scatters. And if you make a kind of random walk estimate, a photon from the center of the sun takes about, whatever, a few thousand years to reach the surface. So actually losing energy for the sun via photons is extremely inefficient. Basically, this basically enhances this process compared to the photon loss by something like 1 over the probability of these two things scattering. And the probability is essentially nil, and the probability for photons is basically 1, and it's multiple scattering. So this makes this very powerful. You can also think of it in a slightly different manner. Photons can only be lost via the surface, so it's a surface emission. This thing can happen everywhere, so it's a volume emission, and volume beats surface anytime. Okay, you can also quantify that, and what would happen? Well, if this coupling is too large, basically you get a large energy loss from the center of the sun. That's where this process is most efficient. To compensate, so the sun center cools. Well, if it cools, it contracts. The sun would burn fuel faster, and that basically the sun would have died quite a while ago. And if you put some numbers to that, basically the luminosity compared to the photons, if you put some coupling in here, if you take the 10 to the 4, remember ALPs discovered 10 to the 7, or didn't discover, limited 10 to the 7. If you put 10 to the 4 here, the luminosity in Axions would be 10 to the 9 or 1 billion times larger than the luminosity in photons. And I picked these numbers on purpose because, well, the sun has a lifetime without any axions of about 10 billion years. So if it's now 1 billion times brighter in axions or loses energy 1 billion times faster, then basically the lifetime of the sun would shrink to about 10 years. And I think we can pretty much experimentally confirm that this is, well, exceeding, the current sun is exceeding this kind of limit. So we can set our naive experimental limit from direct visual observation to something like 1 over 10 to the 4g. However, if you do it properly, if you take into account that the sun has been around for 1 billion years, and indeed, if you look at some other stars, so-called horizontal branch stars, you count them, you measure their energy loss effectively. This really increases by a few orders of magnitude, so you come down to 1 over 10 to the 10 GeV. And that nicely covers all those experimental efforts with one stroke, basically. It's 3 orders of magnitude better than basically this Large Hadron Collider experiment in its current stage. It basically also, because there's more energy involved, it's KeV photons, covers all this axion region over here. Okay. With that, let me just give you one more light shining through a hole experiment, and the one that actually starts to beat this, beat Georg's argument. It's working on it, and there's a future to it. You can do, of course, now also employ this mechanism, because you now know, oh, if there are axions, there would be plenty of them coming from the sun. And those axions would have kilo-electron volt energies. So why not make use of them by just pointing a magnet, in this case a large LHC magnet, pointing it at the sun and waiting for photons to for axions to reconvert into photons and be detected here at some photon detector. And this is a little bit easier. You have this enormous flux, and you only need 1/2 of the experiment. And indeed, it turns out to be quite powerful, because now this cast experiment really goes a little bit beyond this 1 over 10 to the 10. So it's really starting to beat these energy. It still has a little bit of trouble reaching the axion band mass-wise, but that is also improving by using some tricks with gases. But the real improvement, and that's really the last bit, will be the so-called International Axion Observatory that is being discussed right now. It's now a bit of a bigger experiment. You can see it driven here. It's a rather big magnet. And with that, the hope is really to go down to 1/10 to the 12 GeV, so really 2 orders of magnitude beyond those energy loss arguments, and to really probe into the QCD axion band. Okay, and with that, I think I have more than exhausted your patience, and questions.